Welcome to the 2021 Earth Science Week webinar series, Water Today and for the Future. We are pleased to have four outstanding professionals that work with issues of water in human society. Today's lecture is Perspectives on a Crucial Resource, the Importance and Vulnerability of Our Water Supplies. Our speaker is Dr. David Kramer from the University of Nevada, Las Vegas, and President of the International Association of Hydrogeologists.
Hello, my name is David Kramer. I'm a professor at the University of Nevada, Las Vegas, and I'm also president of the International Association of Hydrogeologists. Today, I want to speak on water resources and their importance and vulnerability. I'm going to be emphasizing groundwater because it's the last lifeline we have against the onslaught of climate change and ever-expanding population. Today, I'd like to talk about water in the world, clean water, and the challenge before us. We'll go on to water scarcity, pressures on our resource, and trends. I want to talk about groundwater for a while and discuss why decision makers and the public really don't recognize it. And worldwide water challenges, I'm going to list a few and come up with a couple possible solutions and ways to address these challenges. Finally, I'd like to end with a few of the new frontiers and the opportunities that geologists and hydrogeologists have to make the world a better place. Clean drinking water is a challenge around the world. The United Nations and the World Water Development Report for 2020 estimated that 4 billion people face water scarcity at least 1 month every year. That's over half of the world. And 1.6 billion have economic water shortage. That is, there's insufficient infrastructure to transport water to them. 52% of the world's population will live in water-stressed areas by 2050, according to the United Nations, and 3.4 million people will die each year from a lack of clean drinking water, which is approximately 9,300 people each day. Most of these are children, 2.2 million per year. And these statistics don't even include deaths associated with the lack of sanitation, the lack of hand washing, and the resultant deaths from global pandemics such as COVID-19. Estimates are that approximately 5,000 children die each day from diarrheal fluid loss or lack of clean drinking water. That comes out to be a child every 17 seconds, or during the course of this lecture, over 140 children will die. The United Nations and the World Health Organization have attributed water-related causes to about 80% of all diseases in the developing world. Groundwater is an essential element in our water resources here on Earth. 97% of the liquid, fresh water on Earth is groundwater, and it represents one of our last lines of defense against climate change and our resilience to climate change. It is a shield against ecosystem loss and a defense against human deprivation and poverty. It truly upholds, groundwater upholds the dignity of people on Earth. It's an underpinning of irrigated agriculture and energy production, and therefore it provides food, stability, and economic development throughout the world. It's essential to the health of all living things, and it provides political stability as well. It provides drinking water to at least 50% of the global population, and worldwide, approximately 2.5 billion people depend solely on groundwater resources to satisfy their daily needs. And as mentioned before, in these times of COVID-19, groundwater promotes hand washing in isolated communities and villages. So the question comes up, why is groundwater not recognized by the general public or by decision makers? Why is it something that's not discussed more and not realized as far as its value to the community? Why is it invisible? Well, there's a lot of reasons for this, but primarily it's out of sight. It's below ground surface. It's not visible to most people, and so therefore they don't interact with it, and they don't know how to deal with it. It's difficult to not only understand that it's there or its importance, but what factors affect groundwater and what are the future of groundwater resources are. Groundwater is not taught in our elementary schools, and even in our undergraduate curricula at our universities, many of those curricula don't have these courses in hydrogeology or groundwater. So as a result, many people don't know basic facts about groundwater. They don't know that surface water and groundwater are intimately connected. And if you pollute one, that means that you can pollute the other. Importantly, people don't realize that surface water, rivers and lakes are fed by groundwater, that there is base flow, and some estimates in the world are that worldwide 40 to 50% of surface water is fed by groundwater. Then in deserts and dry lands, slight changes of water tables can eradicate springs that have been around for millennia, that have supported ecosystems and people. Wells can dry up with very, very small changes in the piezometric surface. And so these are things that are not really highly recognized. So one of the global challenges is overcoming scarcity in the world. The chart you see before you shows the ratio of withdrawals to supply. The lighter colors are where withdrawals are much less than supply. The red areas with intense red colors are where there is great withdrawal compared to water supply. You can see that there are many places in the world that have overuse of water. This map that you see before you shows the number of months in which water scarcity is greater than 100%. The green areas have no months. These have no water scarcity, and it ranges up into the darkest colors, which have year-round water scarcity. As you can see, there are many places in the world that suffer from lack of water. According to the Global Water Institute, 7 million people worldwide could be displaced by intense water scarcity by 2030. What this means is migration and movement and displacement of people from their villages and homes. And half the global population that are already living in water scarce areas at least 1 month per year. But this could increase to 4.8 to 5.7 billion by 2050. Most of those people live in Asia. There are solutions. Some of this is new technology. Some of it is basic water conservation and intense monitoring. One of the areas of new solutions is an increase in remote imagery. A lot of the imagery is from space. It's well known for a while that the 2 GRACE satellites can measure changes in groundwater in the Earth by measuring gravimetric differences. There are several other satellites that can help understand groundwater and surface water. The chart you see in the upper right shows a river, and it's a thermal image. And where groundwater, which is warmer, comes into the stream, it's highlighted by orange and light orange colors. so you can see where groundwater is flowing into the stream as base flow. In the middle of the screen is a drone. Drone technology is on the upswing. It's been used for a long time on farmers' crops, as you can see in the lower right. This helps farmers figure out which crops are healthy, which need more water, what the soil water content is. And the picture in the middle is actually a drone with a multispectral scanner that can look at several wavelengths. And this is very, very helpful in scouting for water on Earth. One use we've had for remote sensing is looking at gamma radiation coming off natural geology and potential contaminated areas. The helicopter you see there has an iodide detector that can sense gamma radiation, and you see on the right ground detection gamma sensors. A helicopter will make passes back and forth and look for gamma anomalies in different Earth materials. Here's an example from some work we did in northern Arizona. This site is about less than 15 kilometers away from the rim of the Grand Canyon. It's a uranium mine, and it mines in a breccia pipe feature, is set to mine there. And so we flew over it with a helicopter with a gamma detector, and we also did ground truthing outside the mine boundary. And here you can see the anomalies of uranium, potassium, and thorium over the mine site. A close-up of our ground detector looks like this, and we have Spider-Man to watch over the project here. An example of satellite technology is one project that we have in southern Niger using radar to look for shallow groundwater. Niger is a landlocked country in Western Africa. It has 7 different countries surrounding it. 75% in the Sahara and Teneri deserts. The northern part of the country is the dry part. The southern part that we have outlined here in blue is our study area. It's the wetter part with greater than 300 millimeters of rain a year. Niger has challenges. It's got the youngest population in the world, with half of its population younger than 15 years old, and the population is expected to triple by 2050. It's one of the hottest countries on Earth, sometimes called the frying pan of Africa. Farming there is subsistence farming, and 44% of the people who live there don't have access to clean drinking water. We were looking for shallow groundwater and to better describe the deeper groundwater as well. We looked at 9,000 wells and did geophysics, and looked at the well bores as well. But we also did radar from space with certain algorithms, and we identified shallow groundwater for areas of future development. In this particular map, the yellow areas are shallow groundwater. The light blue is a little deeper. Black is deep groundwater, and red are impermeable geology and rock structures. Another major concern worldwide is the regulation and governance of our water resources. There are many, many challenges in this category, and to list just a few, there's a concern with lack of enforcement of water-related laws and regulations in many places, even if the laws and regulations are good ones. There's corruption, where it's estimated that over 10% of investment in the water sector is lost due to corruption each year, which equates to billions of dollars. I want to give you some examples of other challenges, and these are transboundary water problems. Transboundary aquifers, an aquifer being a geologic strata or containing groundwater that's extractable, and surface water transboundary issues. In 2015, 366 transboundary aquifers were identified, and even more transboundary groundwater bodies as defined by the European Union Water Framework Directive. They underlie almost every nation on Earth. And I want to highlight one transboundary aquifer that's highlighted here. It's the Nubian sandstone aquifer between Libya, Egypt, Sudan, and Chad. And it's one of only one or two that have an agreement between nations on its usage. These transboundary agreements are crucial as we go into the future to ensure political stability. As challenging as groundwater transboundary issues are, surface water is also an issue. One example is the Grand Ethiopian Renaissance Dam that's been built on the Blue Nile, part of the Nile River system, that flows eventually through Egypt. There is no strong agreement at this time as to how the water will be used, and the Egyptians are really concerned over the water they've been using for years, which is really the lifeblood of their economy. Rising sea levels due to climate change around the world are sometimes called the leading edge of climate change, and they can affect saltwater intrusion in coastal areas and particularly vulnerable islands. The freshwater lens under some of these islands has been used for millennia, but is now seeing more use. People who know the Geibin-Hertzberg principle know that for every meter you draw down a water table with pumping of a well, the saltwater-freshwater interface below comes up and upcones 40 to 50 meters in response. This is a significant problem around the world. In addition to coastal flooding with sea level rise, the increased saltwater intrusion can be monitored. A traditional way to monitor this is with measurements of electrical conductivity and saline measurements of the amount of salinity in the water. And here's a chart with an example of those traditional methods used in some wells. In this instance, the land surface in these cross sections is to the right and the ocean is to the left. Salt water is red in this and the fresh water is blue. And this is over a 25-year period. You can see an increase in saline water under the ground surface moving from your left to your right. There are new methods that are being used. Some of them use tracer technology, where you release a tracer to gauge the speed of movement of groundwater, both freshwater, and establish the mixing zone between freshwater and saltwater. Flow meters can be used as well as pressure transducers to help understand this. And one interesting novel way to look at it is with temperature, thermal imaging. Groundwater is usually warmer than ocean water. And this is a thermal image that shows submarine groundwater excursion underneath the ocean from the banks of the beach. And so new methods are being derived all the time and developed, and this is a way to address the problem. One idea that's far from reaching its full potential is the idea of mobile desalination. The idea is to have desalination in ships that could go from place to place with fresh water. They could react to natural disaster, infrastructure failure, terrorist activity. They could avoid bad weather and hurricanes, unlike a shore-based operation. When you do desalination, you create a brine, and the brine, if it's let go in coastal areas, it can be harmful to wildlife, and it's safer to fuse it at sea. This is an artist's conceptualization of a mobile desalination plant, and we have mothballed ships that are being retired all the time, and these could be used for that activity. I don't really agree with this hardest conceptualization. Looks a little top heavy to me, like it might capsize. But it is good in that it shows that you can use green energy to power these things. A lot of our retired nuclear power craft already have the engines in them that could promote desalination. And so this is just one idea that might be a future way that we can address the problem. If you pump too much water out of the ground, you can actually get the ground surface collapsing. And this subsidence can create cracks, fissures, sinkholes, and other problems. This is a shot from an ultralight in South Africa, and it's in a karst area or cave area where we actually have sinkholes. The top two are actually the same sinkhole. One day kids were swimming in this little lake in the sinkhole, and overnight the whole thing drained and left what is in the upper right hand corner. There are little communities growing up all over this area, little villages, and in the bottom picture, these sort of sinkholes are threatening some of these areas. So if you have differential subsidence, you can get cracks and fissures in a major city. This is a particularly bad problem. And in these small village areas, it gives an entirely new meaning to the word settlement. Another challenge is gender bias with groundwater gathering around the world. Typically, particularly in small villages around the world in developing countries, the task of carrying water is left to young girls. And that means these young girls don't get an education because they can't go to school because they're carrying water all day. If you look at the size of some of these buckets too, and you know how much water weighs, you know that this is a tremendous amount of water to carry. And if you look closely, you can see that there is towels wrapped around some of the heads of these young girls who are carrying water. And that's something that we have to address. Another challenge is inadequate sanitation. As communities grow around the world and the population grows, people are forced to live closer and closer together, and they usually draw on shallow groundwater. Well, on the right, you can see a well that people are standing around and a pit privy that's being dug in close proximity. And the idea that sewage disposal and wells are in close proximity can spell disaster for communities as far as different epidemics. This particular picture is from Brent Usher, who used to teach at the University of the Free State in Bloemfontein. Also, water distribution points in the bottom two pictures can be pretty local sources of contamination disease because everybody uses them to gather water to wash dishes and clothes. And so this can be a particular problem as far as sanitation goes. There are literally tens of thousands of organizations that try and do water projects in the world, and sometimes they create more harm than good. And the idea of many of these organizations is let's serve as many people as we can. Let's do masses of people and provide them water. But unfortunately, a lot of these projects are not sustainable. So I would advocate a shift in the paradigm from the number of beneficiaries to sustainability. And I'll give you some historical breakdowns, some information. 21 African nation survey in 2009 to 2011 showed that 36% of installed well pumps were non-functional in these African nations. In the one region of Mali, 80% of the water points were dysfunctional in 2009. and 58% were in need of repair in northern Ghana when I was doing some work there. In much of the economically developing world, low tech is sometimes the best tech. If you have wells that can have their pumps repaired by the local community, they're sustainable. It's estimated in some cases that 1/3 of the wells and pumps for those wells in Africa are inoperative. Also, drilling technology, hand drilling sometimes is superior to other types of technology for drilling.
No, it doesn't indicate. You have to go deep enough. The main problem is stones. If it's very hard stones like these,
these sort of wells are inexpensive to drill. The drilling operation and equipment can be moved quickly from community to community, and it overall can be very, very helpful.
No, it doesn't indicate. You have to go deep enough. The main problem is stones. If it's very hard stones like these,
example of low technology is this well in northern Ghana. This is my graduate student who's doing water quality sampling, Melanie Kroshnick. And that box you see between where the well's being pumped and where the water's coming out is to take out high arsenic. There's sorbent material in that. It's locally available sorbent material, so people in the community don't have to go far, and it reduces the amount of arsenic in the well water as it comes out. Low technology, but good technology. Here's an example where philanthropic people came and put in toilets in a community, but they didn't educate the people on how the toilets were to be used. There weren't any toilet paper factories in the near area, and within a matter of days, it became a worse pollution problem than existed before. The rivers in many economically developing countries are very, very polluted. Sewage is dumped there and people wash and bathe in the same water. This is a shot from South Africa. Again, sometimes lower technology is a better technology. So in our hydrophilanthropy, I think we need a shift in our goals. We need to move from trying to get the greatest number of beneficiaries to sustainable projects that can be used year after year. And I think Einstein said it best. Contamination of our water resources by chemicals is another severe problem facing the world. This is a well in South Africa. I don't think you'd want to drink from it. Most chemical pollution in the world is due to industry and agriculture. In the upper left-hand corner, there is some dumping here of liquids into a dry wash in the Phoenix, Arizona area. The upper middle is low-level radioactive waste being disposed of near the Savannah River plant in Barnwell, South Carolina. Upper right is plain spraying pesticides on crops. There are literally thousands and thousands of different types of pesticides, some long-lived, some more toxic than others. In the lower left, there's a landfill. This landfill leaks, and historically, many landfills, liquids have been dumped that are not beneficial. They form leachate, and that leachate can get into groundwater. Mining pollution can cause acid mine drainage and many other potential problems. This is a coal mine in South Africa in the middle bottom, and a defunct steel mill in South Africa. You see a picture of a fellow picking up coal tar that's seeping up out of the ground. The ground is so polluted, continually coal tar seeps up. In the winter, it's brittle enough to break off. So there are many emerging contaminants One of the ones that's been in the news is PFAS, which stands for per or polyfluorinated aliphatic substances. There are over 7,000 of these, and they're often called forever chemicals because they don't go away. Not all of them are harmful, but many are, and they're in constant use in many different things we do in our daily life. This is a timeline of its discovery in the 30s. It was used for nuclear weapons in the 40s. It was used as Teflon in consumer products and is still used today. Firefighting material, and then there were many, many different uses that have come up. And so these are long-term chemicals which we're now finding are fairly ubiquitous in the United States. Natural background of contaminants is also a problem, and I'm going to give you an example from a study in the Grand Canyon where I've been working for quite a few years. It turns out there's a lot of background contamination. This is a problem worldwide. In India and Bangladesh, there was arsenic contamination from sediments that came off the Himalaya mountains and polluted shallow groundwater and tube wells. One writer called it the greatest mass poisoning in history. So in the Grand Canyon, we looked at background, and it turns out some of the background concentrations were very high. We looked at over 4,000 sampling events historically through the years, mostly groundwater, about 2/3 groundwater. And what we found out is that many of the samples exceeded the maximum contaminant levels, which are the drinking water standards in the United States. A lot of the samples weren't recent. They were old samples as well, before the year 2000. One example to show you what we found, we measured many different compounds, but arsenic, for example, when we looked at all the samples, the thousands of samples, 87% of the time it wasn't even sampled. When it was detected, when it was sampled, there was 11% of the time there were non-detects, and over 88% of the time it was detected. And the kicker here is that when it was detected, arsenic was detected in the sample, over half the time it was above drinking water standards, above the maximum contaminant level, and that was 78 different springs above the MCL of 0.01 milligrams per liter. So natural contamination is a potential problem. From Niger, people don't measure for things like arsenic regularly. And what we found is in some of the soils, there's not only high contents of arsenic, but also rubidium, chromium, and nickel. This is very often along fault areas where there might be hydrothermal fluids that are vertically moving upward. So what are some of the frontiers of hydrology and hydrogeology? Well, I wanted to mention two that I think are extremely fascinating and really get people's curiosities going. One is extraterrestrial hydrogeology and groundwater on Mars. There are ice caps on Mars, and there are many, many different extraterrestrial problems dealing with water that are very, very fascinating. A lot of the planets, the exoplanets that we found around other stars, have large contents of water, according to the spectrophotometry that we get back. Another area where we know very little about subsurface groundwater is below the oceans. And the exchange of water from depths to the ocean itself through the ocean floor is very little known about that. It's occurred to me that there might be some contribution to climate change or effect on climate change with heat flux coming through the floor of the ocean. That's not well measured at this time, and it is a potential future challenge. I think one of the astronauts said it best, Chris Hadfield. He was the commander of the International Space Station, and in a recent trip to Ireland, he said, "I used to think that space was the great exploration frontier, but actually, space is easy. With a bit of math and physics, it's entirely predictable. It's empty. There's nothing there." I realized, looking down from the ISS cupola as I flew around the Earth 16 times a day, that the new real exploration frontier was below the surface of the Earth and other planets. We know so little. The subsurface of our planets is far more complex than space. I had to go to space to understand our lack of knowledge about the planet. If you would like a good reference for future challenges for groundwater, a new text just came out this year called Global Groundwater, and one of the chapters we talk about different issues in groundwater in addition to extraterrestrial and ocean bottom groundwater. These are some of the topics that we discuss. So finally, I'd like to have a brief discussion on what we can do to make the world a better place as geologists, hydrogeologists, and hydrologists. And there are many things we can do, and one of them is to publish and make data available that's high quality to other people, and make use of innovative technologies where appropriate. And this is something that a lot of academics and students do already. We publish books, we publish different papers, and this sort of thing is very, very beneficial to people to find out what's going on in the science. One of the things we all can do is to educate the public and to teach others. And this is not restricted to professional educators. Everyone can teach people about the fragility and vulnerability of our water resources. The upper left-hand picture is a lecture in Bandura University for Science Education in northern Zimbabwe. The upper right-hand picture is in Baghdad, Iraq. It's the Ministry of the Environment, and we're teaching them there how to use water quality equipment. The lower left is in Benin, Africa, and it's students from Notre Dame University doing community education on how to sample for water quality. And in the lower right is a drilling class, a short course with drillers put on by Jasper Muller and Associates from South Africa, and it's supported by a lot of drilling companies there. So these are the sorts of things we can do. Students can make an impact. The higher education system of Nevada has had students going overseas and putting in wells in many, many countries throughout the world. This is one in Kenya in 2004. But the idea of supplying local communities with good quality water is something that everyone can do. You don't have to be an old professor in order to do it. This is putting in rainwater harvesting systems in Guatemala. And again, these are students from the University of Nevada systems. Some people are able to take the time from their work or their school to do extra activities with professional societies and other groups. This can be a very enriching experience. One example is the organization that I'm president of, the International Association of Hydrogeologists. We're a scientific, educational, and charitable organization. We've been around for 65 years. We have thousands of members in over 130 countries. We have regional vice presidents and national chapters around the world. A very highly regarded tops in its field journal. In addition to that, we have educational material and activities. And we have commissions and networks that work on specific problems like groundwater and climate, groundwater and energy, groundwater in coastal areas, artificial recharge of groundwater. We have an early career hydrogeologist network for those just starting out, and a philanthropic arm of our group as well that does work in developing countries. And so you don't have to be a member, actually, even of IAH, the International Association of Hydrogeologists, to be part of these commissions and networks while working toward advancements. We've worked with groups like the United Nations. It's been a real privilege to do that. I actually got to address the General Assembly of the United Nations back in March of 2021. And it's not as exciting as it sounds. I did it remotely with a panel of people. Although the whole General Assembly was there in person, we were remote and not in the room. But it was still a real opportunity and, as I say, a privilege to present that. So there are a lot of opportunities out there, and it can be a great experience if you have the time and make the effort to join these particular groups to advance things. Lastly, I would encourage people, if you have the time, to advocate for the wise use and protection of all water resources. This is something that everybody can do. As professionals, we can talk to our communities. These are pictures of a group of groundwater professionals speaking up on Capitol Hill. And one thing that everyone can do as far as groundwater is concerned is become a signatory of the Sao Paulo Brussels Groundwater Declaration, which came out in September of 2021. It already has thousands of signatories, and you can become one as well. If you go to the IAH website, IAH again stands for International Association of Hydrogeologists. You can just Google IAH.org and find this link there, and you can become a signatory. This declaration was prefaced by a survey of water professionals from all over the world to gauge what people thought was important. And so this declaration will make it obvious to decision makers and to the public the importance and the vulnerability of groundwater. So help make the invisible visible. Thank you very much. I very much appreciate the opportunity to speak with you today.
Thank you, David. That was a great talk. We're going to go ahead and open the floor for questions now. I'll go ahead and get us started with questions. You mentioned several severe issues and challenges with getting adequate water to underserved populations. So what are some recent projects that you're aware of that have really proven to be beneficial towards this water crisis? And could you share any specific examples?
Certainly. Thank you for the question. That is a good question. There are many organizations moving in many different directions. One of the first things you have to do is you have to know what's there. You have to know what your resources are. And so the United Nations actually has a monitoring group that is trying to gather all the information and assess its quality and try and harmonize that data so people can know exactly where problems lie, where we have a lack of data, and where we need more information. There's along those lines, the UN also has a transboundary group. For those of you who don't know, the United Nations set out some strategic development goals. There are a number of them that have to do with many issues around the world and equity and trying to make the world a better place. And strategic development goal 6 is water and sanitation. And the goal is to get water and sanitation for everyone in the next 10, 15 years. It's quite a challenge. And so that's one effort. There are a lot of professional groups doing the same sort of thing. And there are educational materials around for many groups. For example, the International Association of Hydrogeologists has videos and links to different sources. But as far as getting water actually to people, you would be amazed at the number of groups, philanthropic groups, some of them religious, who go out and try and improve things. There are a lot of steps backward for every step forward. For example, one of the very popular things that a lot of people donated to was something called play pumps. It's a device that you spin around in a circle. Apparently, it's supposed to be so children can play on it. They go around and around, and it pumps water out of the ground to a water distribution point. But unfortunately, it's much more expensive than a regular pump. It breaks down more frequently. It's more than 4 times more expensive. And quite frankly, it depends on child labor to spin it around. If you've ever been at a hand pump, it's easier to pump a hand pump or a foot pump than to spin something around all day if you're not playing on it. So as far as distribution of water, I've been involved in looking at remote sensing alternatives, and it looks as though new algorithms for assessing satellite data might help us to identify where there's more groundwater that's accessible, and I think drone technology is on the upswing as well.
Okay, that was great. Thank you. So the next question that we have here is, would you elaborate on geophysical identification and mapping of groundwater contaminants mentioned in one of your slides?
Sure. As far as groundwater contaminants, that's harder. As far as groundwater itself, the imagery that you can get is you can identify faults and fractures where vertical movement of water might be moving up and down. Many times deep groundwater is more mineralized, particularly if it's thermal water. And so that can be identified through aerial surveys of many sorts. There are the ones that I've been using lately is some algorithms with radar technology where you can see shallow groundwater. But again, when we use these, we use them in concert with wells. In Niger, Africa, we looked at over 9,000 wells. We used geophysical techniques as well, and we gathered all the data we could on the subsurface as far as the depth and thickness of aquifers, the water quality of those aquifers, etc. For contamination itself, it's a challenge. We've been using it for uranium surveys. I mentioned some of my Grand Canyon work, and when we were looking at water flow in the Grand Canyon, we were using different tracers and isotopes to see the movement and the vulnerability of groundwater in springs in the Grand Canyon due to development of groundwater wells right outside the park boundary. And we did this with several national parks. Well, what we found is that there was an old uranium mine right on the rim of the Grand Canyon, and below it, we found very, very high uranium, well above drinking water standards. And so the Park Service had this old mine site on the rim of the Grand Canyon as a tourist attraction. And when we found high uranium 2,500 feet below in the water in the springs, they dragged a Geiger counter up on the surface of the tourist attraction and found that it was radioactively hot. So they put a fence around it, dug up the soil and carted it off, knocked down the headworks for the old mine, and now it's getting super funding to clean it up. So I guess what I'm saying is you can tell certain things from the air, but it doesn't replace sampling groundwater in wells and sampling springs and using some innovative techniques. One of the things we've been doing in the last 20 years is developing better and better chemistry and chemical analysis. So we've been able to look at trace element concentrations and more tracers to see where groundwater is coming from. If you look at some of the constituents, chemical constituents of water, you can tell where it's been and where it's going. And for surface water, thermal imagery and many other different types of imagery can tell you things about potential pollution of surface water bodies and the eutrophication of lakes and that sort of thing.
Thanks for that, David. Okay, we have another question. Is there any available technology that can significantly decrease the concentration of naturally occurring selenium in tributaries to a terminal lake in order to protect the lacustrine ecosystem? I don't know if you can touch on that one or not.
That's a really excellent question, and I have to admit right off that I'm not expert on selenium itself. There are several different forms of selenium, and some of them are more mobile than others, seleniate and other chemical species of selenium. For those of you who don't know, selenium is a potential pollutant, particularly for wildlife. It can disturb the embryos of birds and cause major mutations. One very famous case of selenium contamination was in California at a wildlife area called Kesterson, where thousands of bird life began to die because of high selenium. The idea of reducing selenium is really a challenge in many areas because it does naturally occur in many geologic areas. And to reduce it, there are several methodologies that can be used. It depends on the size of the wildlife area. You might be able to do a mixing to reduce the concentration. If you have another source of water, be it groundwater or surface water, that you can mix with incoming high concentration selenium if the aqueous concentrations are too high. In some cases, our options are very, very limited. But as far as treating water, I don't know much about how to treat water to get selenium out specifically. There are certain methodologies to get salts out, generally reverse osmosis and other things that will reduce the salt content entirely of a water body. But as far as just selenium, I'm unaware of those.
All right, thank you for that answer. We have time for one more question. Can you name a few nonprofits that you believe are doing good, sustainable work to bring clean water to communities around the world?
I hesitate to endorse any. I know that there are some that are emphasizing sustainability. I know that some of the water. My own predilection is to not really support water charities that have an ulterior agenda, whether it be, no matter how noble, if they want to promote a religious aspect or things like that, I'm a little bit reluctant to support those, although some religious charities that go overseas for water purposes are just wonderful. There's Water for Life is one that does pretty good work. There is one of my colleagues does some work in Central America. His name is Mike Campana, and his sister, Ann Campana Judge, was one of the victims of 9/11. Her plane went into the Pentagon, and he started a foundation called the Ann Campana Judge Foundation, which supports students doing work to promote water development in Central America. And so there are so many. When I started getting involved in this, I realized there were tens of thousands of water groups that went out. I've written a couple of articles on this, and I think more important is the ways you can go wrong. You can put a perfectly good well that's well designed, that keeps pollution from the surface moving down, like animal droppings from moving down the well. You can design it really well that people may really need it. You can have sustainability where the people can fix it. But one little mistake, like if you put it in the backyard of someone that everyone hates, you can create a water war that lasts generations. And so I've written a couple of articles on hydrophilanthropy gone wrong and how you can blow it. And so it's important when you choose an organization to work with overseas that they know some of these principles as far as how to do it right and how to make it sustainable, rather than endorse any one or two water charities and groups going out and doing things. I would encourage people who are listening to investigate on their own and maybe read one or two articles on how philanthropic efforts with water overseas can be done correctly.
All right, thanks for that. Okay, well, that's about all we have time for today. Thank you everyone for the excellent questions, and thank you, David, for presenting today. This concludes our webinar for today. Thank you very much, David, for sharing your time, expertise, and insights with us. Thank you everyone for joining us today. Thanks again, everyone.
Thank you, everyone.